Okay, welcome to our pre-lab / lab theater video where we're going to focus on the extraction technique. This is in lieu of actually performing the separation by extraction experiment. So in the hood I've got some of the materials set up and I'll walk through what this technique is. Extraction is a common technique for, just like the name sounds, extracting or pulling one thing out of a mixture, right? Like you hear about the armed forces, they have to go in and extract someone who's held hostage behind enemy lines, right? So they go in and they pull them out. When we have chemical mixtures, we want to do the exact same thing. We want to take out one particular chemical or two particular chemicals. That's called extracting. There's a similar concept of what's called washing, right? Washing is like washing your clothes. You want to get rid of the dirt and things off of your clothes. So you can either extract, target one thing out of a mixture, or wash, push several things that you don't want, away, that you're going to throw away. The general idea and the difference is that extract, usually you're keeping what you're pulling out. Wash, you're usually throwing it away down the drain. Okay, you don't care about those chemicals anymore. All right. This piece of equipment that I have in my hands is called a separatory funnel, and it's one of the ways that we do common separations and extractions. There are several other ways to do this, but this is one of the very traditional, old-fashioned, and still utilized to this day ways to do this. The premise of extraction, solvent extraction, is based on what we've learned in chapter 12 about solutions and the solubility that each chemical has. So in the laboratory, as you're described, if a compound A, it looks like that's not showing up very well, if A has solubility in both, let's say, water and another solvent like ether, and we could quantify the solubility as, I don't want to use the exact same numbers in the lab. Let's say that the solubility in water was 0.3 grams per 100 milliliters, and the solubility in ether was 0.06 grams per 100 milliliters. So right away from these two numbers, we can tell that A is more soluble in water, right? On the same volume level, 100 milliliters of water or ether, we can get more A to dissolve into the water, all right? Now ether and water don't mix, so if we put them into that separatory funnel right there, all right, they would separate from each other, with the ether being on the top and the water being on the bottom, because the water is more dense. Okay? If we now add some A into this system, A likes both solvents. And so some A will go into the ether and some A will go into the water. And the amounts will be dictated by these two solubilities up here. So the A will separate itself according to the intermolecular forces, all right? And it will establish an equilibrium constant, a ratio, what we call the partitioning coefficient, the distribution coefficient. We'll learn about these K's in a couple of chapters, but for now it's a pretty standard symbol. That really would just be the ratio of these two solubilities. And we could establish it either as water in the numerator. So let's put the solubility of water divided by the solubility of ether. So it'd be the 0.3 divided by the 0.06, right? Which is 5. All right. Or you could think of this as a 5-to-1 ratio. For every 1 A that goes into ether, in other words, 5 are going to go down here into the water. That's what that 5 means in this case. All right. Now this contains right now a total of 6 molecules of A, as I've drawn it, right? So there's 6 parts, and they separate 5 parts to 1 part, so to speak. The ratio, the 5 to 1, you add those 2 numbers and it gives you 6 parts. That then tells me, well, what if I added 100 parts to here? Well, let's choose 90. You know, if we add, I think I'm still on the camera, if I put 90 A's into here, how many are going to end up in each phase? So in water, it would be 90 times the 5 out of every 6 parts, right? For every 6 that we add, 5 go into water. So all we have to do is multiply by that fraction, 5/6. Okay, so that would be 450 divided, or 9 divided by 6 is easier to do. That's 15 divided times 5, so it'd be 75. So 75 parts would go into the water, and then the remaining 15 would go into the ether. All right, and then you could figure that out as a percentage as well. All right. And what you would see then is that this ether water system would be a useful way to get A out of a mixture. If A is now mixed in with other chemicals and you throw that mixture into here, look at how preferentially A likes the water. Now presumably the other chemicals would not, you know, or else you would choose different organic solvents. That's where this becomes such a versatile technique, because we can mix and match whatever solvents we want to try to fine-tune and dial in just getting A or B or whatever chemical we're after here. All right. But notice we wouldn't get 100% of our A out of that mixture because of this ratio. We're leaving a small amount of A in the ether. So what we often would do is we would repeat this technique again and again, and we would get different sort of crops of this chemical. So if I started with 90 A's, right, one extraction would give me 75 of my A's into water. Then I would take what's left over, and I would be putting 15 that were left over back into it, and I could do 15 times the 5/6, right? And I would get another yield of A, that would be 75. I'd get about 12 more. So between the two, I've gotten up to 87 of my original 90 A's, right? So then it becomes a game of, well, how many times am I willing to do this? You start to get limiting returns. After this, you're only going to start to get 1 at a time, right? And it's not going to be worth it. So usually in an extraction, we would do like 2 or 3 extractions at most, and then we would have pretty close to, depending on this ratio, 90–95% of our chemical extracted. But we're probably not going to get 100% all the time. Okay? So in today's lab, what we were supposed to do is to use the extraction technique to separate a mixture that has 2 things in it. And one of these things is a neutral compound, so it doesn't have any charges on it, and one is an acidic compound, so this is acid. All right? And so the way we're going to accomplish this is to use ether, just like I had in my example here, which is a pretty good solvent for the neutral compounds. It's mildly polar, okay, but not extremely polar. Still got a fair amount of nonpolar to it. And then the other thing we'll use is a solution of sodium hydroxide. It's in water, so it's very polar, all right? And it's also a base. We haven't studied acid-base chemistry yet, but the acid that's in here will love the base that's in here. So even if I put this into ether at the start, which I'll do, when I introduce it to this, all of the acid molecules will jump out of the ether into the base over here, because the opposites attract, so to speak. All right? And that's going to be how we're extracting. We're pulling the acid out of that mixture. The neutral, on the other hand, compound, hates this stuff, doesn't like it. So where is it going to stay? It's going to stay in the ether. And we have pulled apart the 2 compounds from one another that way. All right? And the benefit of the separatory funnel is that it has, like your burettes do, it has a stopcock at the bottom. So we'll have 2 liquids in here that'll be separated, like it'll look like salad dressing that you haven't shaken up yet, right? And then you can just drain out through the bottom, the one layer, And you can stop it and leave the other layer in here and pour it back out the other direction. And so you then physically have separated the two liquids from each other, each liquid containing now ideally one chemical. All right. So the way this would work is what we would have done in the lab today is we would have started with our separatory funnel, and we would have added some ether into the separatory funnel. Okay. So I'll use about 20 milliliters of ether or so, ought to be enough. The ether has a very strong odor to it. The hoods would definitely be on if we were all working with this. I can tolerate it. It's probably not my best interest, but Katie, what's ether? Do you remember what ether is? Because I asked you a special question about it when we studied it during the enthalpy of vaporization lab.
Oh, it's dangerous for people who are pregnant?
It's dangerous for women who are pregnant, actually, ether is. So, all right? It's called a teratogen, okay? There's all kinds of chemical dangers. There are other chemicals that are dangerous to men's reproductive systems, and there's some that are dangerous to women's reproductive systems. So, all right? And so we have to know all these things when we get into the lab. So, all right? So no huffing the ether when you are with child, okay? Just remember that, all right? So we would have weighed out a sample of this unknown. Forgive me for not, actually accurately weighing it right now, but I'll show you what we'll do here. You would have gotten a small sample, not too much, and then it would have gone into the separatory funnel. Okay. And then with a little bit of shaking, that should have dissolved. Now the separatory funnel, the other thing is, listen carefully. Okay, didn't make it there. When we have a volatile solvent like or ether, right now it's generating pressure. Okay, and so it's not generating a whole lot of pressure. But we want to be very careful to vent any pressure that builds up. So it's very commonplace to hold this upside down. I'm pressing the stopcock, the glass stopcock or stopper, against my hand, and then you could just open this to vent it and let that pressure that builds up out. Okay, and that pressure varies from one to another. So now here's my quandary. Both my acidic compound and my neutral dissolved into the ether right now, but I want them separate. Ideally, at the end of this, I would like to have in one beaker the acid component molecules, and in another beaker the neutral component molecules. That's the goal of this lab. Enter the sodium hydroxide. All right. So I would like to have about an equal volume of my two solvents. All right. So that partitioning ratio works. All right. That 5-to-1 ratio that I mentioned earlier. If you don't use equal volumes, you're messing up that ratio, because then you have to kind of reconfigure, for accounting for a larger volume of one or the other. Okay. Now watch carefully. You should be able to see this will sink down through to the bottom. It's going to go down to the bottom, all right, and then the ether pushes up on top. Okay. All right. Now we're not seeing much or anything. These are all invisible. I could have used one of the colored unknowns, and we would have seen this a little bit better. But right now we've got two layers. All right, there we go. Generate a little more pressure now. Okay, you heard that. But this is the technique now. We just need to shake this to try to mix those two solvents together, just like salad dressing, okay? And then we vent them. And it's when they're mixing that literally molecules of ether, which are attached to our chemicals, all right, are being introduced to water molecules, and then we make like a custody exchange, so to speak, all right? Oh, here, I'll hand off the acid molecule to you, water and base, with the base that's in the water, okay? And at that point, it stays in there. Now notice this is good practice. I'm always pointing this away from me or away from other people. I'm not, because it might spit out, right? These are just practical considerations that we want to make sure, we're not idiots in the lab and how we treat each other and our equipment, okay? All right. And this will now separate itself, and I'm now ready to pull apart the mixture. So once it settles down, it's a little hard to see because they're both clear, but I can see the dividing line between the two solvents, All right? And all I need to do is run the bottom layer down out of this beaker. Now notice I took the top off. If I hadn't done that, there would be pressure. I'd start to generate like negative pressure that would want to suck this back in. And ideally, I can stop this system when the line dividing the two is right in the middle of the stopcock. I think I got it there. All right. If you ever make a mistake and too much comes out, just pour it right back into the top and separate it again. I mean, it's nice. Okay, so it's not like it's the end of the world if you do make a mistake, because you could just, in this case, retry it over again. All right. If you don't take enough, it's also okay, because normally I would do a second separation now. Right now, maybe I've gotten 75% of my acid molecules, we said. I don't know what the partitioning ratio is exactly for this, unknown acid that I'm working with. So if I don't know, I'll probably do 2 or 3 extractions to maximize the amount that I am getting. And then I would collect all of the aqueous water fractions together in that case. All right. So I put my water into one, and then I would pour back out my ether fraction into another. So at this point, I should essentially have neutral compound here in ether, because it stayed in ether. And I should have my acidic compound over here in the base. But something happened when I put it into the base. Or when the acid molecules go into the base, they actually react with the base. So they're not acid molecules anymore. They've had their H's, which define them as acids, torn off, okay, and replaced by like a sodium, in this case, sodium hydroxide. So I need to undo that reaction and get my acid back. And so I can just add concentrated acids, or hydrochloric acid, back into this. And what that should do is precipitate out. Because my acid wasn't by itself soluble in water. If I started this over and just put water in here at the start, ether was the first liquid I put in, and everything dissolved into the liquid, right? If I put water in there at the start, nothing would dissolve. Okay, and so it's not until we sort of change the acid that we're able to get it to go into the water. So I can drop some concentrated hydrochloric acid, and I don't know if you can see it. As this drops in, you can see little white puffs forming. That is the acid forming, but it's such small quantities that it's still slightly soluble in there. So if I add enough acid in here, I will sort of overwhelm the solution, and there'll be too much acid and it'll become insoluble. Yep, and it starts to precipitate out of solution. Okay. Making this cold would also help out. That would crystallize that would lower the solubility, because we know temperature dependence plays a role here. So if I chilled this, I would actually get even more of the acid molecules to come out. So it's getting pretty close now. You see how long the cloud hangs around? Actually, it's all forming on the top now that I look at it. Okay. Well, actually, where to go? It's like strange. They're rising to the top. I could see stuff here, and then as I swirl it around, it's kind of looks a little bit like a snow globe right now. I could see the flakes of the acid. That's often a good way to describe this here. But this is how we would then recover our acid, and it would be a simple matter of filtering this. Now we pour it through a Buchner funnel with a piece of filter paper in it, and the crystals of our acid are collected on the filter paper, and this is now the liquid then becomes waste that we don't want. Over here, for our ether and our neutral compound, we just let the ether evaporate. that takes like 20 minutes just sitting around with the hood on. This stuff has a very high vapor pressure, and so it evaporates very easily. If we were in a greater hurry, or we had another solvent that didn't evaporate quite as easily, we would use a technique called either distillation or rotary evaporation, where we basically agitate the sample and we heat it and we expose it to a vacuum. So we're lowering the pressure, which lets the solvent boil more easily. We're heating it, so we're helping it boil off, right? And we're spreading it out. We're making it like in a big thin puddle rather than in a deep, setup. Those are all the ways to speed up the evaporation or vaporizing process there. Okay, so what ideally what you would have done in lab today is you would have weighed out like 1.5 grams of this. You don't know what it is. Okay, so you got a bunch of things to figure out. A, what are your unknowns? That can't happen until the way end, actually. Melting points will be the way to determine the unknowns. Okay, but job number one is to separate them. So you start with 1.5 grams, and the mass is important because we want to figure out how good this separation technique is. We know what the ratio is in here. Okay, so it's been prepared so that we know that for every gram of acid there is 0.5 gram of base or neutral, or 1:1. They're all prepared differently. And what we're trying to see is, do you recover? How much do you recover? So if you start with 1.5 grams, you're always going to lose some, because some is going to stay soluble in these solvents. Okay, all right. So you should not recover a full 1.5 grams. Right, but how much do you lose? One. And then how much of each is one better than the other at recovering the chemical that we're after, is the other part of this as well. All right. So that's why I would have had you wait till Friday. You don't need to do that now, by the way. We could just come to class on Friday at the normal time to take our quiz, and that'll be all we need to do. But on Friday, you would have come back and found your 2 beakers dried out, or your 2 samples dried out, and you would have weighed them to figure out the masses that you recovered, and then you would have scraped some out and taken a melting point to compare it to the knowns that potentially were used in this experiment. All right? Any questions on the technique or anything? No? All right. So I'm sorry that we didn't get to do it. Notice that I did wear gloves. That's pretty common when you're doing this, because the stuff is kind of nasty that you don't want to get onto your hands. Particularly the ether by itself is not dangerous, but it dries your skin out like crazy. And so we're at a time of the year when people's skin's naturally already dry and cracked, and this would just make life even worse, actually. So, and then I think that covered all the odds and ends that we would have done in the lab today. All right. Sorry we didn't get to do this experiment. There's just not enough time now, having gone through this, to successfully accomplish it. So, all right. So you'll have to wait till organic actually to do it. So, all right. Take care.